The research paper discusses the concept of shortest path diffusion, SPD, in image generation, which outperforms previous approaches by determining the optimal corruption procedure through the shortest path in the space of distributions, computed using the Fisher metric. This approach is based on diffusion models that transform input noise into an output image through multiple steps of denoising. The authors hypothesize that the optimal corruption procedure corresponds to the shortest path and contribute by computing the shortest path analytically between Gaussian distributions and proposing an approximation for the non-Gaussian case. The SPD is tested on CIFAR10 and IMOG-NET 64x64, showing improvements on strong baselines without any hyperparameter tuning. The study also explores various improvements in diffusion models, including non-uniform noising procedures, orthogonal wavelets, and the application of optimal transport. The authors derive an analytical solution for the shortest path between Gaussian distributions and propose its application to non-Gaussian cases, highlighting the importance of the Fisher metric in measuring path lengths. Overall, the research contributes significantly to the field of diffusion models by providing a novel and theoretically grounded approach to variance scheduling. The research paper discusses an image generation method using shortest path diffusion, SPD, which involves corrupting images with a forward process to approximate the shortest path between the distribution of real images and an isotropic Gaussian. The authors propose an efficient algorithm for SPD, which scales linearly with the dimension of the data. They validate their method on unconditional image generation tasks using the CIFAR10 and ImageNet datasets, showing that SPD leads to the best quality of generated images compared to similar methods. The paper highlights the importance of the optimal corruption filter in achieving high-quality images and demonstrates the resilience of SPD across different diffusion timesteps. The results suggest that SPD outperforms other methods in terms of image quality, measured by FID, and is nearly optimal for the given parameters. The authors introduce shortest path diffusion, SPD, a novel diffusion model that optimizes data corruption by minimizing the path length in probability distribution space. Unlike previous works, SPD's data-dependent corruption procedure adjusts to the dataset, enhancing flexibility. Compared to IDDPM and IDDPM plus DDIM, SPD outperforms for T is greater than or equal to 100, with better FID scores for unconditional image generation on ImageNet. The key advantage lies in its unique data corruption procedure, applicable to various data types. However, SPD's complexity scales quadratically with data dimension, which can be reduced with a strong prior on covariance. The authors acknowledge limitations, such as the shortest path computation being specific to Gaussian distributions, and highlight the potential for combining SPD with other methods to further improve diffusion models. Theoretical foundations are explored, including Gaussian distributions, theorems, and eigenvalues, emphasizing the importance of Riemannian metric tensors for measuring distances between distributions. This framework is crucial for understanding SPD and its applications in image generation. The research paper discusses the application of shortest path diffusion for image generation, focusing on the diffusion process and its mathematical formulation. It begins by describing the Riemannian metric and the length of the curve for the diffusion process, utilizing the Fisher information matrix as the metric tensor. The goal is to find the curve of shortest length, which satisfies the Euler-Lagrange equation. The paper also discusses the forward process, including a theorem that proves the corrupted vector has zero mean and covariance equal to sigma 1 minus T0. This process is used for image generation, ensuring high-quality images that follow the desired distribution. The time complexity of the power spectrum computation is analyzed, demonstrating that it is quasi-linear and linear, respectively, for the discrete Fourier transform and the fit of the power spectrum. Experimental results show that computing the constants for CIFAR10 and ImageNet 64x64 takes significantly less time than training. The generated images using the shortest path diffusion model are presented, showcasing its capabilities and outperforming other methods in terms of Frechet inception distance.